Okay. So, shall I start?
Yeah. You may start.
Okay. So, ladies and gentlemen, let me present very shortly, shouldn't be more than, say, 5 minutes, the CSProfiler2, which is the collection size profiler 2. First of all, let's jump straight in by looking at some code. Here is a collection. We're creating a collection, an array list, and we'll put it in a list of strings. Now, in a cycle, let's add some strings in here. Just some strings. So we're increasing the size of this collection. Let's query this collection in a very, very simple way and in a more difficult way, in an extended for loop. Now, what we want to see in the end is a graph like this. On the x-axis is some kind of time in changes or queries or whatever you want, and on y-axis is the size of the collection, where the first 3 points should represent the additions to this list. The next point should be the get that we have seen, and the last 3 points should be the extended for loop, thus the iterator. Now, what would we want to see if this code was actually executed twice? Is quite simple. It should be 2 dents like this. First one representing the first run, second one representing the second run. Now, the basic idea here is that we profile collection sizes and then we profit somehow. But seriously, we would like to see which collections are actually used in our code and how heavily, which are the collections where something is really happening. We would like to be we would perhaps like to identify the places where we start by creating these collections, where we modify them, and perhaps we can identify certain regions in time and, let's say, space where these collections are modified and whether they are queried. This could help some optimizations. Also, if we knew by running an actual code and profiling the sizes, if we knew that the collection is never bigger than, say, 100 items, but these 100 items are really there, we could perhaps allocate them in the beginning correctly to this size. Some collections really perform better this way. And in the end, if you want, you can try asking Dima, because from what I understood, he could use this in his loop call graphs. So this is the code, and now we need to somehow get to the collection sizes while this code is running. So, well, the basic idea is put some instrumentation code. At each spot, the collection is either modified or queried, and call the profiler from this spot. I've added also a line to the creation of the collection, and we will see later how this works. Okay, so here is a problem. This is an extended for loop, and the problem is that we're not directly querying the collection here. We're not calling any kind of get. This is because Java internally translates this extended for loop to something like this. So it asks for the iterator of this collection, and then while this iterator has next, it gets this next, and this is the item that we're currently standing at while iterating over this collection. And what we would like to do is somehow get to this call of the next and profile, put some instrumentation code and profile at this spot. Okay, so problem is that this is not only about lists, but also about sets and maps. Because every time we're walking, values, keys, entries, whatever, of a set or a map, there is some kind of iterator inside, and some kind of next is being called. So obviously we need to go deeper. And we're going to JDK directly, where we can see that there is, for example, let's stick with the lists. There is abstract list that has iterator inside. And this iterator has a next method. So what we do, we put instrumentation right at the beginning of this next. But there is a problem. Hashset refuses to cooperate with this approach because, well, a hash set has a hash map inside. The way we solve this problem is that when we create a hash set, when a hash set is created, a new hash set, it creates a small new hash map. We just remember that these two belong together. So there is another question, and that is the question of origin. Imagine that we are looking at these traces that we produce. We'll see them later, and we want to know where this collection originated. Because, well, we would like to go to the place of the source code, and we would like to actually see the place where this collection that we are looking at right now was created. And we can do it like this. Every time there is a constructor inside the JDK of a collection, we'll put instrumentation and we will just take a stack trace. Each constructor of a collection inside the JDK will have instrumentation code, and if we take a stack trace at this point, we will see exactly where this collection was created. Okay, so to do a little situation report here, we can handle modifications, that is additions and removals and whatever, and the querying via the get at the call site. We instrument the call sites and we get to this information. We handle extended force at the next, iterators next, inside the JDK again. And at the same code, we instrument creations of collections so that we can trace their origin. Okay, so let's have a closer look at what profiler would do by looking at a day in the life of a profiler. Okay, so he just sits in here, and there is a query. Hey, check out this object reference that points to a collection or a map or a set or whatever. And what he does is he gets from this object reference its class, something like this is the array list, fine. The size, the actual size of the collection by querying the size method. The thread ID of the thread that was responsible for running this piece of code. And some kind of time when this event occurred. And he just dumps it in a big fat log file. This big fat log file looks like a series of snapshots. I would call it snapshot for now. Snapshot looks some kind like this. So it is a textual information containing first class name and the object ID that actually caused this log to be performed. Then there is the thread ID. This is some kind of number that we can aggregate or whatever and look at a single thread, for example. Then there is the Unix timestamp in milliseconds. This is the big ass number here. And then there is the actual collection size in the end. Alternatively, if we start the tracing with a certain option, we will get a stack trace of this moment when this logging happened right beneath this line in the big fat log file. Okay, so we have a log. What we will do with a log? Okay, graphs, of course. This is, well, you can actually see it. This graph comes from the Decapo benchmark, from the end LR benchmark, I don't know. Okay, Decapo is the suit and LR is the specific benchmark. And what you can see here, x-axis again is the time, y-axis is the size, and each line corresponds to one collection. You could perhaps see a legend over here, but it's not that impressive. The point is that we see that the collections here are created and then cleared, obviously, because their size abruptly drops to 0. Let's see another graph. Okay, it can be seen here. This is the PMD benchmark from the same suit. It can be seen that there are a few collections that are actually being modified and queried. Querying is always this straight line. Modification by adding is incrementing the size. Going down means removing something from the collection. I have to stress that the time scale isn't the same for all these lines. This is time in actual modifications or queries. This means that if a collection does something right now, it gets the time 1. And if some other collection does its first modification in 1 hour, it will still get the time 1. This is why some of the lines end sooner than the others. So we see that we have a few collections that actually stay at a reasonable size here. And we have a few collections that are first created up until something like size 35 or 40 perhaps. And then we start querying them in the end. So, to sum it up, we can use this profiler to run any Java program. It doesn't need to be anyhow specifically modified. We will just use modified JDK, and we will profile this program dynamically with the CSProfiler2. We get traces of collection sizes in a big fat log files, and we profit. Do you have any questions?
What generates the profit?
No idea there. That's why there are these 3 question marks. Right.
Why is big fat file? Big was not enough. It should be also fat. Also.
Yeah, well, the stack. If you start tracing stack traces and saving them to file, you get megabytes in seconds.
Why is it called Profiler 2?
Because the version 1 couldn't handle the modified JDK.
Can you go to the graphs?
I can't interpret these graphs, I'm so sorry. You can just look at it or
I'm
enjoy
just
it.
wondering, not on that graph, but on the second graph, what it means that there is a straight line, linear line that goes up, and then there is change of color, right? So,
This is because there are more lines in the same spot.
so one collection stopped at number of,
Exactly. It's
35 and one.
let's say 34.
and the
Right.
highest collection has
36.
never been queried. It was
Exactly.
on the-
Looks like that.
looks
So
like
this is kind of
useless.
information that you can get from running this benchmark. You have a collection that you never queried. Is it necessary to even add to it?
So
It's
that,
like-
that seems like one of your question marks could be replaced with this is
Yes.
a use, right?
Yes.
So is it accumulated threads also for this graph?
Sorry.
Like all the collections on these different threads?
Yes, this is all threads running here.
Looks like PMD is doing something wrong.
Yeah, but on the other hand, it looks like there is something correct, and we can, for example, create the collections that it uses on size 5 right away, and we know that we won't run out of this.
But but how did you run this backup? Did you say minus size?
This is the normal size. of
Yeah,
PMD.
minus is a large.
Yes, correct.
What is PMD doing?
I have absolutely no idea.
Because what you see the baseband at the bottom, to me looks like quite a lot of collections. They stay between 0 and 4 elements big. So does it make sense to have a collection that only contains a few elements? So maybe it operates on 3-dimensional vectors or something like that. I have no idea, but it's a bit
We need
strange behavior.
Do you filter out all these collections that are at the beginning with all the
yes.
so it is
Yes.
away? And here somehow, if there is a hash set, you don't reproduce the map corresponding. It's only
Yes,
one.
it goes under the hash map.
So you're only in this picture representing collections that were created in application code.
Yes, because until in the pre-main there is a call start profiling now, and anything that happens before, as per our communication, is just is not locked.
But if later on, let's say I'm saying new JButton, and if JButton internally is kind of heavy and it allocates a collection, that you will capture.
Yes. Yes.
How do you flash the information? It's like the shutdown hook, you flash everything, or it's like periodically?
Flashing is in a shutdown hook, and I'm just writing to a file all the time. There is no optimization in the sense that I would keep a buffer and then flush it at once.
How much slowdown do you have if you don't use stack traces, roughly? 10 times slower, 100 times slower, 1,000 times slower,
Didn't check this.
But more or less
Yes.
by perception.
roughly? You have to wait a long time for this?
I would say There is a long time in the beginning when everything is loaded. I feel this is just my feeling that the benchmark takes a time to start, the JVM takes a time to start, and when it's running, I would say 5 to 10 times slower, just by rough, very rough estimate.
Yeah.
Okay.
That's great. Nice work. Where can I buy it? Is it on SourceForge?
Sorry, this one? No,
Yeah.
do you want it there?
Oh, might be a good idea.
Okay. Let me create a to-do then.